So if we use A to split, we find out, okay, we just end up with two subsets where each subset shares the same label. So we can see that when A is 1, when we end up with 100 positive example, right? Because for this trunk, right? For this particular trunk, there's 0 negative examples. So all examples are positive. For A is 1, right? And for A is 0, we have 100 negative examples. So now we end up with 2 leaf nodes, right? The tree only has level 1. So you can see that we don't need any more feature to do the further split. But now what if we use B to split the data first, and then then do we need to further split on subsets, right? So if we use B, we found out, okay, for B is 0, okay, there are indeed purely labeled examples which are 50 negative examples. But for B is positive, B is 1, right? Here and here we have 100 positive examples and 50 negative examples. So they are definitely mixed, right? So we do not end up with leaf nodes here, and we still need to split the data further. Now we have to use A, right? Because we only have 2 attributes. So if we further use A to split, okay, now we got 2 leaf nodes, right? So we have A is 1, B 1 is 100 positive examples and 0 negative examples. Although this empty set is although this is an empty set, so we need to adopt the most common label here, right? So now look at these 2 results. Which attribute should we use first? A, right? Because A ends up with a smaller tree. This tree generated by using A first only has 1 level, right? And this tree, which use B first and then A second, has 2 levels, right? And much more and many more nodes than the first one. So definitely we should use A, right?
Is the A tree smaller because the A equals 1 and B equals 1 has 0 examples? Therefore, when A equals 1, it will be positive 100% of the time.
The A tree is small is just because the size of A is smaller than the size of this. So you can see A only has 1 level and B, and this tree has 2 levels, right? Yeah. And this tree has 2 nodes, and this tree has 4 nodes.
Yeah.
So if you have 0 examples, why don't you just have like a question mark for your label? You know your label even though you have 0 examples.
Yeah, that's what we just mentioned in the algorithm step, right? If you have an empty subset, you cannot just delete the branch. You still need to append a leaf node, but you can use the most common label in the parent node, right? Which is I could just take a look at here, right? So the parent node here in B is 1, right? B is 1, you have 150 negative examples. 150 examples. You just choose the, oh sorry, this is a pebble. If it is 0, meaning that you should choose the positive.
So if a node is pure, does that mean it just branches into leaf nodes?
Yes.
Okay.
Yes. Well, I think I would say, okay, this is most pure, because purity later we'll see that it is a continuous measurement. It's not just a 0 or 1, because later we'll say a more complicated examples. Okay, so now let us make a few change of this data set, right? Suppose I have 3 examples here. So in our case, just mentioned, right? For A is 1, B is 0, only have 0 examples, 0 negatives. But now what if we have 3 negative examples here? And then we want to ask what attributes should we choose first, right? So similarly, we still look at, we just test manually, right? We use A to split data first and say what happens, and use B to split data to say what happens, right? If you use A to split, A is 1, now it's not purely labeled because we have 100 positive examples and 3 negative examples, right? So this is not leaf node. And for A is 0, we have 100 negative examples which are uniquely labeled, right? A negative, as negative, right? And now if we use attribute B to split data set, what can we get, right? And B is 1 here and here. We got 150 examples total, where 100 are positive and 50 are negative. And for B is 0. We have a 53 negative examples. So now we can say, okay, right now, both A and B, the two trees, will need to continue to grow, right? Now I want to ask, right, which one do you believe is better? Which attribute do you believe is better? I heard A. Why?
It's more balanced, I guess.
Yes. Right. So here it is a little bit more complex, right? So although both results, right, the subsets splitted from A and subsets splitted from B are not totally pure, meaning that they are non-lineals, but the subset from A is more pure in terms of labels than the subsets generated from B, right, or splitted from B. So if we adopt the greedy heuristics we just discussed, right, we should believe using A to split data set is better because the labels of the subsets are more pure than the subsets generated from B. And suppose you have extra features like B and C and D and so on, right? We believe that, okay, based on this more purely labeled subsets, you continue to do this, you're gonna end up with a smaller tree sooner.
It's more pure because the tree is balanced?
No, it's not tree balanced, it's labels are balanced. Labels are not balanced. The label is more biased. So when we talk about purity, we're talking about the label purity. It's not about tree structure. Right? So you can see, using A to split data, you end up with two subsets, right? So the right side, of course, is they share the same label. They have achieved the most purity. But for the second side, right, although it doesn't. The labels are not unique, but it is dominated by the positive label. Right? But if you look at the subsets from B, right, the right-hand side, okay, is pure label, but the second one, you can see the labels, different labels are much more balanced than this one. So in terms of label purity, this subset is better than this subset. So we believe that indicates the quality of using A to split data is better than the quality of using B to split data.
Because A is less balanced than B.
Yes. Okay. The label is more biased, meaning that, okay, we believe using a smaller number of steps in the following, we're going to end up with a tree. If we use B, because this is much more balanced, the labels, right, it might end up with more branches than those in the growth of the tree. Does it make sense? Okay, great. So intuitively, we're gonna still choose A to split data first, right? But obviously, we need a way to quantify this, right? We need some kind of measurement to quantify the purity, or at least the improvement of purity, using this feature to split the data set, right? And we just run the features and pick up the best one, right? And then, what kind of measurement should we use, right? So we're gonna first talk about the information gain. So information gain originated with the ID3 algorithm. It was invented by Quinlan. But later we'll see that there are actually other alternatives. It's not necessary to only use information gain. So what is information gain? It is based on the fundamental concept. In information theory called entropy. How many of you have heard of entropy? Okay, great. So entropy is used to measure the uncertainty about the labels in a data set. Right? So given a set of examples S, so we can calculate entropy, which measures how uncertain I feel for the labels in S. So obviously, if your labels are kind of balanced, very balanced, I'm most uncertain, right? So if you have half of the training examples, half of the examples are positive, half of the examples are negative, I will be most uncertain about the labels, right? Because you have half chance to be positive, you have half chance to be negative, right? That means I don't have any knowledge actually about the labels, right? But if your labels are quite unbalanced, right? Positive dominance the negative labels, like 90% chance you got positive, only 10% chance you get negative, right? Then your uncertainty is much, much less. Right? So let us look at the definition first, right? So the entropy for a set of examples is defined as follows. So we're gonna first calculate the proportion of the positive example, denoted by P plus, and proportion of negative example, denoted by P minus. And P plus P minus is 1, right? And the entropy is computed as minus P plus logarithm P plus subtracted by P minus logarithm P minus. And why should we put minus sign in front of them?
Because the log becomes minus.
Yes. Remember, this P positive and P negative are between 0 and 1, right? If you take log, it is negative. I want the entropy to be non-negative, so I put minus sign in front of that. So in general, if we have a k labels, right, and the probability of your example takes label k to be pk, right? So you got have k probabilities p1 to pk. Then the entropy is given by this. And so it's just a summation over minus pi logarithm pi from I equals to 1 to k. A straightforward extension of the binary case. So now let us look at how the entropy reflects the purity. So it's actually, if you view the purity of the labels as one set of the form, entropy is essentially the other side. So if all the examples belong to the same label, the entropy is simply 0. And some, for example, if P positive is 1, right? And we know that minus P positive logarithm 1 is just 0, right? But someone may be concerned about this term because it's 0 times log 0, right? Don't worry. Although if you just calculate at 0, it is undefined. But in information theory, people define this one as a limit. So you can view it as x times logarithm x. When x takes the limit to 0, you can show that this limit is 0. So that means, okay, you can simply view, but it's not very rigorous, as this term is simply to be 0. So that means, okay, if all the examples belong to the same label, the entropy is 0. And all the examples belong to the same label, the set actually reaches the maximum purity, right? In terms of label. In terms of labels, all the labels are the same. Of course, they are most pure, right? By the same time, your entropy, which represents the uncertainty about labels, is the smallest, which is 0. Right? Because all the examples have the same label, you are 100% sure about the label. Right? You have 0 uncertainty about labels.
So you would want the entropy to be as less as possible, close as possible to 0.
Yes. Yes. But now we can see how the entropy reflects the purity, right? And on the other hand, if P plus equals to P minus equals to 0.5, you can show that entropy reaches maximum, which is 1. So, and P plus equals to P minus 0.5, meaning that, okay, you have half examples as positive, half as negative. You are most uncertain about labels in this data set, right? Because they have equal chance. At the same time, you reach maximum entropy, you actually have the worst purity, right? Right? You're balancedly, your labels balanced perfectly, right? It is very mixed, right? So the purity is worst. So now you can see when your uncertainty reaches maximum, your purity is the worst, right? When your uncertainty or entropy is the smallest, your purity reaches the maximum. So that's why we call it two sides of one coin. And similar, so here we'll give you a more intuition about the entropy value. So we can see that if two labels are balanced, totally balanced, right, 0.5, 0.5, your entropy is maximum, which is this blue bar. But if one label dominates the other, the more dominant of that label, the smaller the entropy, which indicates the better the purity. Right? So similar observations apply to multiple labels. Right? So here's how we compute the entropy for multiple labels. So you can see that if your distribution of those labels are uniform, meaning that each label shows up with equal chance, you got the largest entropy. On the other hand, if you have one label whose probability dominates all the others, you have a much smaller entropy, which indicates a much better purity. So overall, entropy directly measures uncertainty. High entropy means high uncertainty, which reflects low purity, right? Because the more uncertainty, the more evenly your labels distributes on the data, right? In the data. On the other hand, like, if you have low entropy, means that you have little uncertainty about labels. That means there must be some label which dominates others, so we have a high purity. So naturally, we can define our change of purity after using one attribute to split data in terms of entropy, right? So here's how the information gain is defined. So the information gain of the attribute A is the expected reduction in entropy caused by partitioning on this attribute. So meaning that, okay, before I use A to split data, right, I got entropy of the labels in the current set, right? And then after I use A to split, I got several subsets. I calculate some kind of enriched entropy of the splitted subsets. Now I subtract them. That indicates the reduction of entropy. So the reduction entropy indicates the increase of purity. Remember, right? The larger the entropy, the smaller, the worse the purity, right? The increase of the entropy indicates the decrease of the purity, and on the other hand, like the decrease of purity, the reduction of the entropy indicates the increase of purity. That's the idea of the definition. So now let's look at this further in more detail, right? So we first compute the entropy of the current data set, current whole data set S. And now, after we use A to split data set, we got a bunch of subsets, right? SV. And V enumerates all possible visiting values that A can take, right? So for each subset SV, we compute its entropy. But now we're going to calculate a weighted average according to the size of SV. Why? Any thought? Yes?
Well, S, if subset V is the same size as subset S, then you haven't reduced it.
Yeah, exactly. Because we need to consider the importance of different subsets according to their size, right? consider you have one subset which contains like 1,000 examples. The other only contains 10 examples. And of course, the purity of that 1,000 examples is more important than the purity than those 10 examples. Right? That's why we should weigh the entropy of each subset according to their size. And of course, we need to normalize this weight because this is actually a weighted average, right? Normalize, we need to ensure that each weight is between 0 and 1. Their summation is 1. Okay? And so we divide the actual size of each SV by the total size of the data set, which is S, size of S. So now, like as we just mentioned, like, the expected reduction of the entropy is actually expected increase in purity after using A to split data set. Right? So the definition of information gain is here. Okay? So any question regarding this definition?
Would you ever set like a threshold and just stop if the purity is high enough and say, to optimize your tree size? Instead of like going all the way down to
That's a good question. That's about post-pruning. So we need to discuss about it later. Let us, for now, just assuming, okay, we're running ID3 algorithm. Each time we use information gain to rank those attributes and pick out the one who has the largest information gain. So remember, largest information gain is actually the maximum reduction of the entropy after splitting, right? In other words, it means the maximum increase of the purity if we use this attribute to split data set. And we use that attribute to split data set and get and then end up with a bunch of subsets, and then we do this again and again until we reach the leaf node. But yeah, you're right. If you do not limit the growth of tree, you end up some other risks like overfitting, which we're going to discuss later. Okay, so now we have we were clear about every detail about this algorithm, right? Now we're going to use this concrete data set for practice. Throughout running this example by our hand, we should be ready to implement the ID3 algorithm with information gain heuristics. Okay, so again, we have this 14 training examples collected in the past 2 weeks, where each row corresponds to a training example, recording the 4 weather features, all temperature, humidity, and wind feature, and by decision, play tennis outside or not, right? Positive or negative. So we're gonna manually follow the ID3 algorithm and information gain to create the tree. Right? So first of all, we need to split the whole data set, meaning that we need to choose the attribute for the root node, right? The global root node. So to do that, we need to compute the information gain of using each feature or attribute to split data set, and then compare those information gains, pick up the one who has the largest information gain, right? So remember, to compute the information gain, we need to first compute the entropy of the whole data set before splitting, right? These are shared by all the features, right? If you look at the definition here. This entropy S has nothing to do with A. So we can first calculate the entropy of the current data set, the whole data set, once, right? And use it for each individual feature, right? So what is the attribute for this whole data set? So just to look at positive ratio and negative ratio, right? So we have a 9 positive examples and 5 negative examples. So the positive ratio is 9 over 14, negative ratio is 5 over 14. Then we'll just use this formula to calculate entropy, which is 0.94, right? Then we need to look at the expected entropy of using each attribute to split data set. Right? Let's start with the all-log. So you can see that by using all-log, we actually can split this data set into 3 subsets, right? When all-log is sunny, S, all-log is overcast, O, and all-log is raining, right? So let us first look at the subset where all-log feature is sunny. Right? We found out, okay, there are 5 examples here. And from these 5 examples, we can see that 2 2 of them are positive, the remaining are negative. So the positive probability is 2 over 5, and negative probability is 3 over 5, and just substitute the P and N for their actual values in the formula of the entropy. You get entropy 0.971. And then we should look at the overcast example, where all take the value overcast. You have 4 actual examples here, 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 and here. And it's good to see that all the 4 examples are positive, meaning that you have reached the maximum purity. The entropy is simply 0. And the third subset we're going to look at is when outlook is raining, right? So you got 5 examples here, 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 here. So all of these 5 examples, 3 are positive. So you have a P positive 3 over 5, and negative probability is 2 over 5. You just calculate the entropy, which is 0.971. Right? So now we have the entropies for all the 3 subsets, splitting from the all. Right? And now we'll calculate the expected entropy, right, by weighting the size of the entropy, the size of each subset, right? So we know that the outlook, the sunny subset has 5 examples, size is 5, overcast 4, and rainy 5. So their weights are 5 over 14, 4 over 14, and 5 over 14, respectively, right? You just do this weighted average of the corresponding entropies, we end up with 0.694. And now the information gain is computed by subtracting the entropy of the entire data set by the expected entropy of the splitted subsets while outlook. And we end up with 0.246. So just to finish one computation, just computation for all of features. We need to follow the same procedure to compute the remaining features. So for humidity, right? So we can first look at humidity. And for humidity, we actually have 2 subsets, right? When humidity is H high and humidity is normal, right? So for humidity high, this subset contains 7 examples where 3 are positive, 4 are negative. So the entropy is 0.985. And for humidity normal, which is the second subset, by using humidity to split data set, we have 7 examples above, right? Where 6 are positive and 1 negative, which is quite pure, right? Which is quite pure, but it's not a unique label. Yeah. So the entropy is 0.592. So now we calculate the expected entropy by weighting each entropy of the subset with the size of the subset, which is 7 over 14. 7 over 14. Actually, they're equally weighted, right? So you end up with 0.785, which is expected entropy of this splitted subsets. Now the information gain is computed by subtracting the entropy of the entire data set by the expected entropy, which is 0.1515. So the remaining gains are quite mechanical. I won't repeat here. So we can just follow this procedure to compute. Right? So you can compute that the information gain of using wind feature to split data set, you get 0.048. And the information gain of temperature is 0.029. Now, we know the information gain of every candidate entropy. Right? So which one should we use to split? Outlook, right? Because outlook has the largest information gain, meaning that if you use outlook to split data set, the purity of the labels of the subsets will increase, will be maximally increased. Okay? So we finished our first split, right? We split on outlook. Right? So now, by using outlook, we got 3 branches and we got 3 subsets, right? And what is the next step? the next step is continue the splitting, right? Following ID3 algorithm. Remember, ID3 is a recursive algorithm. So now we're going to recursively call ID3 to split this subset, and this subset, right? Until we reach the leaf node, right? So let us first look at the second subset, where all the alloc feature is overpassed. We found that all those examples are labeled as positive, meaning that we can stop here, right? We have reached the leaf node, so we create the leaf node, and we give the label as positive. Right? And now, the remaining two subsets, their labels are all mixed, meaning that we're going to continue to split them. So let us first look at the summing examples, meaning all the examples whose all value is summing. So we've got 5 examples where 2 are positive, 3 are negative. Okay? So remember, now we can only choose the attribute from temperature, humidity, and wind. Why? Because all has been used, right? It needs to be kicked out from attribute set. And more intuitively, if you look at all value here, it's all summing, right? You cannot use all of the split anymore because every example shares the same value. So we follow the same procedure to compute information gain. Right? So first, compute the entropy of this whole subset. Remember, now this subset only have 5 examples, right? So your p positive is 2 over 5, and the negative probability is 3 over 5. And then you just replace them into the formula to compute the entropy, and then you calculate the expected entropy. It turns out that, which I'm going to omit the computational details, which is I believe is quite mechanical, right? So by using humidity to split this subset, you end up with information gain being 0.97, and using temperature, you end up with 0.57. Using wind, you get 0.02, right? So now, which attribute should we use to further split this subset?
Humidity?
Yeah, humidity, right? Because humidity has the largest information gain, so we're gonna use them to split. Okay? So if you look at the results of using humidity to further split this set, you'll find that you end up with 2 purely labeled examples. Each subset share the same label, right? So for high humidity, among those examples, they are all negative. So you create a leaf node and use the label negative, right? And for all humidity being normal, and all the examples are positive, so you create a leaf node, and the label is positive. And do we finish with this part? Be careful, it's not yet. Because humidity can take 3 possible values. Okay? High, normal, and low. So we need to consider a third case. Although among these 5 examples, there are no examples whose humidity is low. That means the corresponding subset is empty. But we still need to create a branch to consider this case. And of course, because the subset is empty, we do not know the label. So just look at the most common label in its parent here, which is negative. Right? So we assign a negative label for this label. And now the remaining, once we finish the construction of leaf nodes here, we return to this leaf node, or return to this intermediate node. From the computer science point of view, is essentially to pop up stack. Right? Pop up stack, you return from the last core of the recursion, and then you pop up, go to this core, and then you enumerate, then you switch to this subset, right? The third subset where the outlook is ring. For all the examples, and here we have 3 positive and 2 negative, right? And again, we need to calculate the information gain from the remaining features and pick up the one who has the largest information gain. And here we're going to choose wind. And if you use wind to split this data subset, you find that you end up with 2 subsets where each subset is uniquely labeled. So you got strong wing for those examples. All the examples are negative, so you create a leaf node with negative label. And for weak wing, you have a label, yes, a positive. So now we have finished the construction of the decision tree by following the ID3 algorithm. So hopefully this concrete example will be enough to showcase how this algorithm works. Right? So I highly recommend everyone to do this manually by yourself, so that it will help you deeper understand the algorithm details. Otherwise, I mean, sometimes you feel, okay, this whole algorithm list is so simple, but when you do it, when you execute, it might not be as simple as you thought. Okay, any questions so far?
So this doesn't guarantee the maximum information gain overall, right? So this is a greedy algorithm, and it's the
Yeah, let me put it more rigorously. It doesn't guarantee the globally maximum of the, well, if you have some smallest tree, if you have some measurement about the scale of the tree, it doesn't guarantee global smallest. But it just but we can I can tell you empirically, it nearly always gives you some relatively small tree, and it's very fast.
I was wondering, for the game, what's the point of calculating the entropy of S in the game?
Oh yeah. So before you split, like at this node, right? You got this 5 Sonic examples, right? So I want to choose. I want to further choose an attribute to split it, right? So and then I need to calculate information gain of using every possible attribute, right? So then I can first compute the entropy for this, and then I compute the expected entropy of using each attribute to split data set, and subtract this entire entropy by the expected entropy. Any other question?
It's not possible that use the same attribute at each level. We use mean and humidity at the same level. It's not a problem.
Use what in the same level?
We shouldn't use humidity and in the same level for array.
Oh, it's not necessary. It's possible. Like because it's possible. Like remember, when you have this sun example, you have a rain example. They are separated. So they're not influenced on each other. So you might have like humidity. You might have a humidity to serve as the attribute has the to have the largest information in here, but also have the humidity have largest information in here. It is possible. But it really depends how your examples or labels are distributed in different subsets. Okay, great. So to summarize our learning decision tree or decision tree learning, so first we need to be clear decision tree is essentially a data representation. It's a hierarchical representation of the data. That's it. Right? And our algorithm, our ID3 algorithm, in essence, is a greedy heuristic, and we just recursively call itself to partition the data set until we reach the leaf node. That's it. Okay. So now let us, the remaining, I think the most important things about decision tree are done. The remaining thing about decision trees are a few extensions and tricks in dealing with the practical problems. So we're going to talk about several variants of decision trees. How do we handle examples with missing feature values? How do we handle non-volume features? Actually, we have briefly covered this in a previous lecture last week. And finally, we're going to introduce a very important concept called overfitting, and how do we avoid overfitting, and what's the problem of overfitting. So, as we just discussed, right? So the whole algorithm framework ID3 is quite generic, except that how we choose the best attribute in each step is kind of open. Why? Because we only talk about information gain principle, right, or information gain heuristics. And we use information gain to measure the increase of the purity after you use a particular attribute to split the data set, right? But someone may ask, right, why should we just use information gain? Is there any alternative to information gain, which can also measures the increase the purity? The answer is yes. Right? So I will introduce two simple variants, which are widely used in practice for reference. Okay? So the first one is called majority error. So you can view the majority error is an alternative to the entropy, which also reflects the purity. So what is majority error? So suppose the tree was not growing below this node and the majority label were chosen, what would be the error? To be more concrete, at some node we have 15 positive and 5 negative examples. What is majority error? Following the definition, the majority label is positive, right? So now I use this positive. I label or predict all the examples here as positive. How many mistakes do I make?
25%.
Yes. So we have 5 mistakes, right? So the error will be 5 over 20, which is 1/4, right? So now let us think about why majority error reflects purity. If all the examples have the same label, what is majority error?
0.
0, right? Because you use majority label, it's the correct label for every example. You have a 0 error, right? And what if you have half positive, half negative? What is majority error? 50%, right? So because whichever label you choose, right, you're gonna mistakenly label the remaining half, right? So your majority error will be half. And my question is, does the majority error, is the majority error possibly be less than half?
No, it never can be because whatever we're doing the majority of, that is expected to be at least 50.
Yes, exactly, right? Majority label actually takes at least 50% of the examples, right? That means the biggest number of mistakes you made should be less than half of the examples. So the majority error won't be less than half. So half is will be bigger than half. So half will be the biggest majority error, right? So now we can see when the majority error is 0, it's the smallest, but the purity is the largest, right? The purity is the best, right? You have all the examples who have the same label. You have 0 majority error, but have the best purity. On the other hand, when majority error is the largest, it is half. Then your purity of the labels is the worst, right? Because you have half positive, you have half negative. It is perfectly balanced. So accordingly, we can define the majority error gain, right? So we calculate the expected reduction of the majority error, which indicates the expected increase of the purity. Remember, the larger the majority error, the worse the purity. Or in other words, the smaller the majority error, the better the purity, right? So the decrease or the reduction of the majority error also indicates the increase or improvement of the purity. So we can calculate the majority error gain instead to rank those attributes as selected. So this is one alternative, right? And second alternative is even more commonly used. I think it might be even more commonly used than the information gain. So which is called the Genie Index. So for binary case, the Genie Index is simply 1 subtracted by the sum of square of the p plus and p minus. If you have a k labels, then it's just 1 subtracted by the sum of square of all those pk's. And pk is the probability you take label k. So first of all, because the summation of p plus p minus is 1, or summation of everything, all the pk's is 1. If you take square, it actually reduces the skew, right? So this value is always non-negative. Right? And then let us do a concrete calculation first, right? Suppose you have 15 positive and 5 negative example. The Genie Index is computed by 1 subtracted by 5 over 15 squared, subtracted 15 over 20 squared, which is 3 over 8. Right? This is just follow the definition. So first of all, we can see that the Genie Index is always non-negative, but when the Genie Index is maximum.
I think this is when the positive and negative examples are balanced.
Yes, you can show that. This is actually quite easy mathematical problem. You can use what kind of inequalities. So you can show that this one achieves the maximum when p plus equals to p minus, or every pk is the same. So you see that the Genie becomes maximum. But at the same time, we can see that this is where the purity is worse, right? Because p plus equals to p minus, meaning that they are half, right? Half labels are positive, half labels are negative. The purity is worse, right? On the other hand, when the Genie Index becomes 0, yeah, one of the probability becomes 1, right? And all the other probability becomes 0. 1 subtracted by 1 is just 0, right? But this is when the purity is the best, right? All the examples have the same label. So now we find another measurement which reflects purity, right? Which is a counterpart to the majority error, which is a counterpart to the entropy. So accordingly, we can define our Genie Index gain, right? So we know that the larger the Genie Index, the worse the purity, or the smaller the Genie Index, the better purity. So the decrease of the Genie Index indicates the increase of the purity, right? We just follow the same framework, compute. Before we use A to split S, we got the Genie Index for the whole data set, and then after we use S to split data set, we got the Genie Index for each subset. We calculate the weighted average, which is the expected Genie Index, right? We calculate their difference, which indicates the improvement of the Genie Index, which indicates improvement of the purity after using A to split data set. So now we have got two alternatives to information gain, but those alternatives are easily incorporated into the ID3 framework. Right? So in your homework, you'll see that you are required to implement all the 3 variants, and you can test them on real data set and see if using the 3 different heuristics will end up with the same tree, or what's the variation in the tree structure. That's very interesting. But by the way, it doesn't guarantee like all the 3 heuristics will end up with the same tree. This does not guarantee. Okay. The second important topic is about how to deal with missing feature value. Right? So this is pretty common in practice. Right? Believe me, in the future, if you want to apply machine learning in real data, you'll see your real data is really ugly and really noisy, including many missing attribute values. You have to complete them first. Right? So suppose we have 15 examples, like in our previous discussion, we assume we have 14 complete examples right? Now we have 15 training example added, but the outlook feature is missing. And now how do we leverage this, still leverage this example? Or in other words, how do we incorporate this 15th example into our ID3 algorithm? Remember, ID3 assumes all the examples, their attributes are complete, right? So I have to guess some value for this missing attribute before we throw it into the ID3 algorithm.
Use the probabilities according to the label. So the label is no, and most of the time it's going to be something with no.
Yeah, I think your point is very good. But let us start with a simpler strategy. Yeah, most common. Yeah. So our first strategy will be simply look at the existing training examples, right? We just look at the existing training examples where they do not miss the output value. We just look at the most common value. We use that value as a guess, right? And then we fill this blank, right, with the most common value in the existing data. Then we can go ahead to run our ID3, right? This is the first strategy, most straightforward. But someone may argue that this is kind of too rough because it ignores the label information, right? Remember, this is a negative label. So you might ask, why not? We just look at the negative examples in the existing data, right? For all the negative examples, whose outlook value is there, we just look at the most common value as a guess for this missing attribute. And then we fill the gap and then we run ID3. This is obviously feasible, right? But sometimes you might feel it's kind of balanced. It depends on your choice. No guarantee which one is better, right? If you look at the number of the examples who have the same label, who don't miss the outlook value, this subset is too small. You might think, okay, let me just expand the range. I just look at all the examples, no matter what label it is, and what is the most common value to fill the gap. Right? But this just gives you two options, which is pretty simple. But the problem is that when we complete this missing attribute value, we only complete with one value, right? Once we choose one value to fill the blank, we just ignore or reject all the other possible cases, right? Suppose I guess this is summing. Then I will ignore all the other cases where the outlook can be overcast or can be rain, right? Conceptually, this is not good. So is there any way such that we can consider all possible choices of this value? Meaning, including both the case for being sunny, being raining, and being overcast. That brings us to a more elegant way. That is, we use some fraction counts of entropy values. Right? We can look at the distribution of different entropy values in the existing training data, right? We know that, okay, 5 are sunny, 4 are overcast, and 5 are raining, meaning that for this missing feature, it has 5 over 14 chance to be sunny, 4 over 14 chance to overcast, and 5 over 14 to be raining, right? So how can we integrate all the 3 possibilities? So a trick here is that we're going to break this single example into 3 examples. But we assign some fraction count in front of them. So this fraction represents the probability that the outlook takes the corresponding value. So why should we put this fraction count? Because we do not want to duplicate examples, right? We want the total number of examples is consistent, right? So if you add up these fractions together, you still end up with 1, meaning that, okay, in total we still incorporate 1 more example in the training data, right? But here, by varying the fractions, actually we consider the different possibilities. This outlook takes the corresponding values. Then the remaining thing is that, okay, we end up with 3 fractional examples, but they are all complete. in their attributes. We just threw them into our ID3 training algorithm. And then run ID3. That's it. But someone may concern that, okay, how do I deal with fractional counts, right? So see that it seems kind of like not very intuitive or some even uncomfortable, but the whole procedure, the whole computation is exactly the same. So don't feel strange. Just to do it as what we defined, what we discussed in ID3, right? So first, we'll add one more example, right? We break them into 3 fractional examples, right? So now consider, now we have like 14 plus 3, 17 examples, right? But if you add up all the fractions, there's still 15. And remember, all the existing examples, their fraction count is 1. So now, if we calculate the information gain for all of them, see, because right now we still need to select an attribute to split data set. We need to calculate information gain for all of, for temperature, for humidity, for wind, right? So let us use all of it as an example. This is a previous split, right? Without these incomplete examples. Now, when we add the incomplete example into the computation, right? That means we add 3 fractional examples into the 3 subsets. So now, we should be aware that now the total size of each subset now becomes a continuous number. It's not a integer anymore. So this some example whose fraction count is 5 over 14. So it is added into this subset, right? And this overclass example added into the second subset. So the size will be 4 plus 4 over 14. And there's a ring example whose fraction count is 5 over 14. So the total size will be 5 plus 5 over 14 for this whole subset. And now we just calculate the positive and the negative probability, right? So for this some example, because incorporation of an actual 5 over 14 negative example, so we have 2 positive. Now we have 3 plus 5 over 14, right? And similarly, for this envelope example, because of incorporation of this 5 over 14 negative example, so our total negative examples now becomes 4 over 14. Remember, previously we have 0 negative example. And for ring example, okay, our number of negative example now becomes 2 plus 5 over 14. Okay? And the calculation just exactly the same. So the p positive is just 2 over the total size, 5 plus 5 over 14, right? P negative is 3 plus 5 over 14 over 5 plus 5 over 14. You got p positive, you got p negative, you calculate the entropy. That's it. And similarly, you can calculate the entropy for this overclass subset and range subset, and then you calculate expected entropy, right? Remember, when you calculate expected entropy, you should weight each subset, each entropy according to the subset size, right? That subset size now is a non-integer size. Right? Remember, for the Sunny subset, the size is 5 over 5, or 5 plus 5 over 14, right? And overclass 4 plus 4 over 14, range 5 plus 5 over 14. But if you add them together, the total number of samples is still 15. Right? It actually doesn't change the number of training examples. It doesn't vary the number of examples. It's still reasonable. So we have a. So the question is how to compute the majority error. I want to ask this. So look at this subset, right? What is the majority error? Any thought? So what is the majority label for this subset? I mean, what is the majority label? Yeah, it's negative, right? Because remember, this is not non-integer number, but we can compare it. We can compare it, right? So this one is bigger than this one, meaning that the majority label is simply negative, right? So if you use this majority label to make predictions, right? So we're gonna make 2 mistakes, right? So the majority error will be 2 over the total size of this data, which is 5 plus 5, 14, right? So that's the majority error. So you can use the exactly same procedure to compute the majority error gain and Genie Index gain. All the computation applies the same procedure. There's nothing to change. The only thing you need to change is that you need to get used to that. You need to feel comfortable with that. Okay, so we haven't talked about in the training how do we incorporate the missing attribute examples, right? But what about in a test? What about in a test time, you are given an example, you don't know the outlook feature. Remember the testing procedure that you're gonna test from the root node, you're gonna find a path until you reach the leaf node and then provide a label, right? So now if you have an incomplete example, how do you conduct that test? How do you give the prediction? Yeah, first, for these 2 strategies, it's still usable, right? You can first guess the missing attribute value by looking at the most common value in the training data, right? But of course, the second strategy won't work because we don't know the actual label of the test example, right? That's something we want to predict. But we can also use the third one. And we can use the third one to take the outlook attribute as the example again, right? We got 3 fractional test examples, right? And for each fractional test example, we got some prediction. Now we just look at which label has the more weights. Right? So to be more concrete, right? Suppose now you're given a test example here. We don't know the outlook feature value, right? And we don't know label. This is something we want to predict. So we break them into 3 fractional examples, and the fraction is the probability that the outlook takes each value, right? So if we fit this particular example, we got positive prediction. If we fit this example, we get negative prediction. And if we fit third fractional example, we got positive example, right? So now we see, okay, the positive labels, so positive predictions got 5 over 14 and 5 over 14 fractional counts. We add them together, right? We got a weight for our positive prediction, which is 10 over 14. But for negative prediction, we got 4 over 14. So which one should we use? Yeah, we should use the one who got the prediction who got the larger weight, right?
What would you do a tie there?
What?
If it was 50-50 there, we could choose.
Oh, that's the tie. That's I mean, if you don't have any prior knowledge, whichever label you can use. But if you have some more domain knowledge, your own judgment, you can choose accordingly. Okay, thanks. Let us stop here. So I think you should feel comfortable. You have all the tools and the knowledge to start doing homework once. So start early. And homework on Thursday we'll finish the remaining parts of the decision trees and go on to introduce the basic concept in computational learning.